Hey guys, my name is Randall Walden. I am currently a graduate student working under Dr. Notmani doing research. We're going to talk about anisotropic diffusion today. So what were you planning on coming up in this class? So I will introduce the basics of anisotropic diffusion and using... Pardon? Good. And using scale-space operations of egg detection in graphical images, basically saying I'm going to lead up to anisotropic diffusion, talk about filters that lead up to it, and then actually apply it later on very the primary focus the primary focus is getting intuition of how, when, and where to use anisotropic diffusion. I know I'm probably butchering that word, but bear with me. I'm going to have less focus on the mathematical procedures, which won't be obvious for the very first few slides, because it's a lot of math. Any student can ask any question at any time during this class. In addition, additional links for additional information will be provided at the bottom of the slideshow. So, for example, not on this one. Next one. First, we're going to talk about isotropic diffusion, which is the spreading of something more widely. That's the definition of diffusion. We're going to talk about the heat equation first, then a brief review of the Gaussian blurring, and then comparing the two, deciding which one's better. Then we'll talk about anisotropic diffusion, the problems with conventional blurring methods that we discussed thus far, Gauss-Berg's model, and then Perona-Linke model, that one, and possible improvements of it. So these are the links I talked about. So if you want to go more in depth of what this is and how I got this stuff, you can come here. First, we're going to talk about perfect isotropic diffusion. And this is basically saying that if I take an object in 3D space and I drop it, it will diffuse perfectly in all three directions. So you can think of it like this: if I have an ideal liquid and I have a point charge at the very center, it should disperse equal amounts of energy up, down, left, right, every single direction, right? This is actually scalar. Speaking of the heat equation, to me it was easier to think of it in three-dimensional space first before I thought of two-dimensional space. This is essentially saying the exact same thing. If I have a closed system, this right here, heat inside the system will be equal to the heat that I disperse through the system, right? So it all stays within the system. Pretty box, right? This is actually different than what we kind of done with Gaussian diffusion right now. So if you remember from Gaussian diffusion, one of the main issues that we had is that when we hit an edge and that awesome little matrix went over to it, we had to put zeros because we interpreted it as black, right? We fixed that kind of by smearing the image out or flipping around. You can kind of fix it in a few different ways. This is it in two-dimensional space. So notice I just have X and Y at this point. I don't have a Z domain. This is pretty good because I can interpret heat as being brightness. So 255 as being super high, super bright, and 0 being super dark or not bright enough. This is kind of how you apply it to images. So if I have something that's 255, it will evenly disperse over. So if I have a sigma times a Gaussian pulse, then I just get a Gaussian spread, right? It's a heat diffusion image. Is this a linear function? Anyone? I'll give you a hint. The hint's up there. It says linear heat equation. So.
Yes.
Yes. Cool. Awesome. Please note that since this is linear, I can actually apply convolution to it and a few other neat little tricks, and it's also stationary and shift invariant. I might be talking a little bit quickly, so if you guys want me to slow down and kind of go more in depth for something, please tell me, because the only thing slowing me down are these questions. Okay. I think we've done something similar to this in analog, but just in case you don't really know, this is my system. So let's say I have an image. I have X and Y, right? I take a picture of the image or recording on the camera. Then I'll do quantization, which is H, my degradation of the image. From that image, I also incorporate noise. This could be salt and pepper noise, Gaussian noise, any of that kind of noise. And I'll get G of X, right? So how would I write that in spatial domain? This is kind of an aside, but does anyone have any idea? Cool, don't worry, I got it for you. So G of X of Y, this one right here, will be equal to my original image convolved with my degradation, right, plus my noise, right? Now let's try the same thing for restoration. Cool. Well, how would I get my I prime, we'll call it?
So G times the F.
Yeah. So G convolved with F should give me I prime, right? Cool. Bonus. Okay, so we're going to do a quick Fourier transform. For those who don't know Fourier transform, I'm just bringing it over to the frequency domain instead of time domain. This will be useful because right here, the linear heat equation has a few things. It's not an ODE just yet, it's a PDE, so it's a partial differential equation with respect to y, x, and t, right? So I'm going to switch over to the Fourier domain and get u, v, and t again, right? So now I only have one thing for my ODE, right? So if I take a derivative of both sides, or antiderivative, or whatever, and do this with respect to time, I'll get an equation. This shenanigans, right? Correct? Cool. The solution of ODE, y. Why is this an ODE? I went through it really quickly, but I'll click on the next one because the term is used in contrast with a partial differential equation, which might be with respect to more than one independent variable. In our case, our only independent variable is this. So we only have one independent variable.
I will just summarize the question first. The question is, you have some equation after you got to the Fourier domain, you have an equation which is still equation of three variables, right? You have variable t, you have variable u, and variable v, right? So you have equation of three variables. Why we call that equation ordinary differential equation, right? Not partial differential equation, but ordinary one. This is the question. Because you have three variables. Generally, when you have more than one variable, it's partial differential equation, right? This is how you get to partial differential equations. You just add in more variables and more derivatives of different kind. Now, here you still have the same three variables, I mean different but still three variables, and I call it ODE. Why ODE? And the answer is that the differential equation is defined by the derivatives that you have in that equation. And the only variable with respect to which you have derivative in that one is t, which is time or iteration, whatever you call it. Which means that this is actually ordinary differential equation, and compared to the derivative, u and v are constants for you. They might be different, but still constants compared to the derivative part. So all of those are not functions or of derivatives of t, or derivatives of u, or derivatives of v. You have only one derivative with respect to t. This is why this is ordinary differential equation.
That probably made a lot more sense. Okay, cool. So we all understand this so far? So let's talk about the future reference. This is heat diffusion in three-dimensional space. So you see high points kind of go down, shrink down lower space, blah, 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 blah. So remember that equation that we just went over? I think it was e raised to the negative u plus v squared? No, I tried to do that. Well, we're going to do an inverse Fourier transform on that and get it back into time domain. Cool? Linear heat equation is actually very similar to the low-pass filter of standard deviation. All right? Anyone want to tell me why exactly? Okay. So basically, it's going to disperse to equally all the way around it. It will actually, so if I have a point right here at the very center, it will give less heat to a point far away from it, right? Kind of the same thing for Gaussian. I'm going to have a point right at the center, high, and give most energy to the points around it. So it's kind of blurring it out.
Do you understand why this one is actually the same thing as Gaussian filter, or just blurring? The formula itself. Pay attention what this formula is saying.
If something raised over.
So technically, this is just solution of the differential equation. Okay, so you have differential equation. You did inverse Fourier transform and got that solution for f of x, y, and t, which is technically the solution of the differential equation. And you've got convolution of f at x, y, and 0. So what is x, y, 0? What is f at x, y, 0 time? This is your original image, unblurred original image, because this is at time 0. You haven't done anything to it yet. It's your original image. This is f of x, y, and 0. Now you're convolving it which is operation of what? What is convolution? This is filtering,
Multiplication and
right? This is what we call filtering. This convolution is some kernel. What kind of kernel we've got here?
Something similar to Gaussian.
It's not similar. This is Gaussian. This is exactly Gaussian. This is this form of Gaussian. But Gaussian with specific sigma, which is a function of t, right? You see that 1 over 2 square root of pi t, and then something divided by 4t. And in Gaussian, what we have the same thing. Instead of 4t, you have twice sigma squared, right? Instead of 4t. Other than that, it's the same thing. So technically speaking, you can replace that t with sigma squared divided by 2, and you will get exactly that Gaussian. Just pick your sigma, which means sigma equals square root of 2t in that case. And this is completely equivalent to just blurring by Gaussian, which is just regular linear filter that we learned about some lectures ago. That's exactly what it does, heat equation. So when you evolving heat equation on image, you get the same thing as just blurring it with Gaussian filter.
Okay, cool. We're going to go over a small MATLAB example. If you guys want, you can follow along. I think the information is available on Canvas.
So you can download the file, MATLAB file from Canvas.
That's very. Okay. So here's the heat equation. I made it over here. So heat blur. This is me just applying the equation. So let's run it real quick. T stands for how many iterations I'm doing. So for me and my program, I'll do 4 iterations for every 1 step. So if I say T is equal to 1, I'm actually blurring it 4 times. I'm going over and over and over. Right? So when I say 0.25 right here, that means I'm only blurring it once. You can hardly tell it's blurred at all, right? Down here, I'm doing T is equal to 1, so I'm blurring it 4 times. Over here, I'm doing T is equal to 2, and I'm blurring it 8 times, right? You can progressively tell that it gets more and more blurry. Let's see if I can zoom in, see if I can make it any better. Yeah, there we go. So if we were to look right here, I guess, yeah, shorter should be fine. Okay. You can see that it barely diffuses anything. It gets more diffused, right? Where's my mouse? There it is. Okay, now we're going to do a brief review of Gaussian filtering real quick. So, if you're listening to Dr. Mahoney, Gaussian filter. Same thing, since it's linear, I can actually convolve it with my image. So same application, same everything. Notice how I'm saying linear, because once I hit nonlinear, I can't really convolve it anymore. So the appropriate transformation would be this, and that's the 2 sigma he was talking about earlier. For more information, you can hit up this place. Making the size of my Gaussian kernel, depending on the size of my Gaussian kernel, I can actually alter how much it diffuses, how quickly, right? So if I make my Gaussian kernel really big, I'll get a lot of diffusion, a lot of the noise is going to be erased, compared to if I have a very small Gaussian diffusion, I'm going to keep the original image intact for the most part, but I still keep all that noise, so it's kind of counterintuitive. Please note that T is theoretically sigma 2, though in C implementation is the size of the Gaussian filter. Okay. So this is my basic Gaussian filter. I'm sorry, it's super bright. If you look at the very center, I'm putting a lot of weight at the very center, and I'm putting a lot less weight on the sides, right? So it's a simple 5x5 Gaussian filter. Taking the Gaussian kernel, that thing, you can set the center to be x, x is equal to 0, y is equal to 0, which is basically saying start at the very top left, right? And then I can tick over as I do that, right? Rate of change function. So I'm just slowly moving my Gaussian kernel over, doing it over and over again. So like we discussed with Dr. Namak, I believe. Brief view of the derivatives, right? So if I like to think of it as acceleration and velocity. So the L'Hopital's transformation is basically the change of x over y. So you can say that what else sounds like the rate of change, velocity, and then L'Hopital squared is rate of change, which is acceleration, right? So the rate at which these things change. Let's talk about a MATLAB example for Gaussian blurring. So here's where I'm altering different sizes of sigma, which is the size of my kernel, right? So here's with a 2x2, that's where a 4x4, here's with an 8x8, right? MATLAB kind of messes with the kernel size, so depending on how big my kernel is, references that little pattern, like 5x5 I showed you, it sets it up itself. It has a special formula where it actually calculates which one it should take the most weight for. So 4x4, 8x8. Now, I can also do this one. Awesome, MATLAB, awesome. This is nice charcoal art. I like to collect art. A lot of art. The next example will show a Gaussian kernel with varying sizes. So a 4x1, for example. I think it's a 2x4, or a 4x1, a 1x4, a 1x8, and an 8x1. And it kind of shows the lines of the image. So like remember how we saw, if we got a box and we moved it across the screen, we got these weird stripes going on, like filter. This is what it does. So here's an 8x1. You see how it has a weird mark going horizontally. Here's a 1x8, it's going vertically. 1x4. Or horizontally, 4x1 vertically again, right? Okay, here's just a close-up of blurring, if you guys are interested. Right. So top left-hand corner, top left-hand corner of the image, I'm just showing the original image with all the noise in it, and after I blur it with the regular Gaussian kernel, which is a 4x4, I believe, in this case. This is completely optional. Under the gradient, if you want to play it, it takes like 10 minutes for me to play it because it's really computationally hard. It designs a image in 3D space and actually shows you the gradient. I won't go over that because it takes way too long. Okay, let's compare the two. What do you think will happen? Which one do you think is better? Anyone? There's actually no question to the class.
Same.
Same? Are you sure? 100%.
9%.
90%. Okay. So let's have this original image, right? It looks pretty cool. We're going to pay particular attention to this spot, right? I'm just pulling one spot out of this entire image because I just want everyone to kind of pay close attention to it. So let's filter it. Anyone notice anything different between the two images? Give me a hint. So remember that MATLAB won't show this. Yeah, MATLAB won't show this properly because it will actually smear the image for you because it already recognizes this. But for our case, we turn that situation off. You can actually see where it's saying, okay, my Gaussian kernel is on the outside, right? So it registers this as black. So you get this weird edge all the way around the image that's just completely black if you look at it, right? But the same thing doesn't happen over here in heat diffusion. Anyone want to know why? It's because everything is self-contained in that image. So like, remember how I said the heat that's in the image diffuses all the way across? So sooner or later it will all turn gray or whatever the average color of this is. If I keep on running over it, over it. Again and again and again with multiple iterations. So why is this important? Well, it's kind of important. The reason why I say it's kind of important because you kind of solve the issue with Gaussian blurring just by moving it left or right. So why do we use this? Gaussian's filter is faster, same result for the infinite domain, right? Why do we need the heat equation at all then? Anyone? Open question. Anyone can answer. Solomon, you seem like smart. I have the answer. I'm just messing with you. Don't worry about it. Boundary conditions are more appropriate for images. So if we have infinitely large image, yeah, Gaussian would be perfectly fine. It's faster, it's nicer, it looks prettier. But once I get to those boundaries, it starts flipping out just a little bit until we do some fancy filtering for it. What function is minimized by the linear heat equation? Okay. This is a hard question for me too, don't worry. It's a placeholder. I'm going to pass this to Dr. Dotmani because I will admit when I don't know an answer. Dr. Dotmani?
Okay, so technically you saw that function already in one of the previous lectures. Technically think about that like that. What is blurring? Blurring is basically reducing the differences between nearby pixels, right? This is what it does. Which means it kills edges to some extent, right? And more blurring you're producing, less edges you have left. If you're doing blurring with average on all pixels, what do you expect to get? Just average color everywhere, just flat image with average gray color, nothing else. If you kind of put in mask which is infinite and constant, so you're using for each pixel, you're using average of all neighbors, and you're using all of the neighbors, right? So you'll get every pixel the same value, because you're using all of the pixels technically every time, for every neighbor. Now, what it means to minimize something. So you need to think about some sort of cost function, which you are minimizing every time when you're doing some sort of blurring. So what you are actually minimizing. So we talked already about derivatives, right? Derivatives of the image, and we know that magnitude of the derivative is somehow proportional to closeness to h. Not exactly proportional, but related, I would say, to h. Higher the jump in the derivative, more contrast you have in that edge, right? So bigger jump is, more the difference between black and white or white and black, more the step edge you have, more clear edge you have. But if you blur it, which means this is what you are doing by that equation, right? You're minimizing that contrast. So what kind of functional relation you can minimize here? This is clearly, I'm not proving here anything, it's just I can prove it mathematically, but we will not at that point. What we are minimizing basically is magnitude of the gradient, right? Because magnitude of gradient locally at every point becomes slower and lower, more and more blurring you're doing, right? So if you take in that magnitude of the gradient or norm on the diff of f function or on gradient, okay, norm of the gradient, it will be smaller and smaller. So this is the functions that you are minimizing by heat equation. And it could be proven using some other methods, because how you find what function, what cost function is minimized. You just solve in some specific set of equations. You have tools for that. And then you can prove that if you're minimizing the magnitude of the gradient, what you will get is heat equation. So it will be result of that minimization. So you can get to that heat equation not just by throwing it out of nowhere. Okay, you will say like, look, heat equation is the same thing as Gaussian filtering. This might be interesting theoretically, but practically who would use it? Boundary conditions, yes, maybe, but really, would you like to use it like heat equation just to solve the problem of boundary conditions? Like a few pixels around the border? Is that really that important? I mean, to use so many iterations and computations and and complicated maths just to solve the border? Clearly not. This is not the reason to use it. Now, by defining minimization cost function, something that you want to minimize, and then to have that one as solution, has much broader applications than just border conditions and boundary conditions on the image. More than that, when you're doing something like that, when you're minimizing something, you can solve much wider range of questions in computer vision by the same approach, getting to completely different equations. Sometimes you don't want blurring, sometimes you want something else to minimize some other process or some other cost function, right? And you'll get to completely different partial differential equation. It's used in segmentation, it's used in classification even problems, in many other problems. This is just educational to learn it through heat equation, because this one is the simplest one, and it's linear, and you probably saw it somewhere in physics before, if you took any physics. Because this is very popular equation and easy to imagine how heat dissipates. Okay, it's easy just to imagine that you have some hot point here, and then you let it just flow all over the place, so it will probably get hotter around that point and less hot at the middle of that point, right? This is how heat behaves. So we can imagine it. And this is why this part is more educational, but we will soon see very direct application of the same idea to much more interesting blurring process.
Still unconvinced of the heat equation, or the importance of the heat equation? Yes, you are. Let's go to a MATLAB example real quick. Sorry for blinding the group over and over again. So, this is a Gaussian filter. This right here is the heat blur. As you can tell, you can't really see it with this image because it's actually stretching it out. What we talked about the filter about 2 classes ago, where this image is actually stretched out on this border. I just wanted to show you that it is applicable to actually do it like this. Also, that last point was like a joke. But, a brief noise review and problems with filters to this point. So, just kind of what we've gone over. What's the main drawback of this picture? Noise. Image noise. Why does it bother us?
Features are not.
Features aren't distinct, and you know it looks visually like crap, right? Visually as humans, lots of details, renders the image unfit for most of our desired image implementation manipulation filters. So I think I'm about to go over Sobel. Do you remember the line tracing? If I was to line trace this, how do you think it would look?
Like a hot mess.
Right, like a hot mess. So we're looking for efficient method of noise removal that is able to clarify the image, right? So noisy image after I apply some filtering to it. Motivations for filtering. What do most filters we've gone over have in common?
Remove noise.
Most methods we have gone over typically apply a blur to the filter to the image, which hopefully results in a smooth, noiseless product. Not always true, but you know, that's the principle of most of our filters that we've gone over so far. Why do we filter? To create a product with less noise levels. This is a better starting point for image-related algorithms. Right? This next example, please notice that the grass clear is almost completely homogeneous, which is, in our case, considered to be the desired effect. It is because the smoothing operation is very useful in highly homogeneous regions, since it scales down the complexity of the region to a simple bulk of very few discrete brightness levels. So here's my original image. Right? You can consider this area right here to be noise, because you see how many, to do a Sobel filter on this, I would have a bunch of little lines jumping around everywhere. You can consider trees to be noise, all this stuff to be noise. After I apply a blur to it, I know it looks kind of hard to look at, but you notice how this is actually a single color now, or almost, right? You might have some dark regions, but if I was to apply a Sobel filter to it now, I'll get a much more distinct outline of trees, maybe the river and whatnot. I won't get too much outlines here except when I get color changes. This is because the smoothing operation is very useful in highly homogeneous regions, since it scales down the complexity of the region to a simple bowl of very few discrete brightness levels. I already said that, I'm sorry, it's on 2 slides. While being a popular tool, Gaussian paths has its downsides. What are they?
Edges. I mean,
Yeah, so loss of details and smoothing across boundaries, right?
Yeah.
Along with the edges as well, right? So basically what this says is that whenever I blur something, if I get to an edge like a distinct edge like this, if I took a picture of it, it'd actually blur across it. It wouldn't care, right? And in that sense, I actually lose the detail of my image, the important parts I want, right? The first is kind of expected for a trade-off. However, the second is kind of problematic. With no clear boundaries, image segmentation can be difficult. Here are some examples. So here's a nice, pretty image. Has noise and whatnot. We're going to pay attention mostly to that top left-hand corner. Maybe it's left, I guess. For you guys, it's off to the left. This is a picture of Pacific U.S. Navy Air Base during World War II. Now we're going to apply a Sobel filter to it. Notice that this is kind of what I was talking about earlier with the grass. I'll get a bunch of junk everywhere, right? The results, the correct edges of the photo contains many false edges, not very good for edge mark making products. So you can still make out that this main edge right here is actually still a runway and whatnot, right? Still have a lot of definition, but to a computer, it makes completely no sense, right? So we're top left-hand corner again, right? And you just can't really understand what's happening. If we smooth it using Gaussian, right? Gaussian or heat, doesn't really matter at this point, right? This is our resulting image. All right, now we're going to apply the exact same filter. I forgot to make you look at the top left-hand corner again. Looks a lot better, right? I don't have as much of that random junk, that real freckle noise that's just kind of right there that's just randomly tracking it. Many of the false edges are smooth. Unfortunately, some of the true edges are also smooth, right? So I think the best example would be, let's see, this right here. See how that's an edge? Gaussian blurred. It's not really there anymore. Using the linear smoothing gives especially poor results in more coarse image. So the more noise there is, the less of an image I'm going to get. So like that Taj Mahal I saw at the very beginning, if I was to smooth that, it would look completely terrible. A blurring already makes an image a lot more coarse, right? Just because the meaningful edges in a coarse image would be smoothed as much, that is hard to determine where the real meaningful edge is actually located. So I have more MATLAB examples. Everyone should close their eyes. Is this the right one? Yep. Classical edge detected after smoothing. So, as you can see, this is my original image. This is my image using the Sobel filter without filtering, right? I have a bunch of the grass. I have some of the buildings back here. Well, though I kind of want the buildings, but the grass is just falling out, right? Smooth the image, and then using the heat blur. I actually use a heat blur for this one, not the Gauss. Doesn't matter. And then I use the edge detector again. If you look at it, I get a lot more definition. I don't have all this noise happening right here. These are actually important lines. For example, if I was to take this image, lay it on top of the original image, and enhance, then I would give an original image with enhanced features in those distinct areas, right? I don't think I'll really go over that in this lecture, but that's just something you can do. It's nice. For more MATLAB examples resulting in edge detection. Grossberg's idea. Okay. Smoothing algorithm has to stand up to the following criteria, right? Causal, no sporadic details would be generated while passing from finer to coarser scales. This basically means that I don't cause more problems than there are, right? I don't. What's a causal system? Okay. I can have a system that predicts the future, basically, right? Cause effect kind of thing. Be localized at each resolution. The region boundary should be as sharp and concise with these cinematically meaningful boundaries at the resolution. Yeah. So that basically means that once I hit the boundary, I'll just slow down. I shouldn't blur as much right there, right? Simple. Piecewise smoothing at all scales integration. Smoothing should occur preferentially over integrational smoothing. So interregional, sorry. I forgot to put a hyphen right there. So essentially what that means is that if I had an area that is black with a few spots of freckles, it should consider that to be interregional and smooth that area a little bit better than it would be at an edge which is not interregional, it's cross-regional. Smoothing that respects this criteria should get better results, right? So, for example, let's do this. Remember that part right here? We can see a little bit better right here, right? Because I'm slowing down once I get right there, not paying much attention to it. So how do we achieve this? Yeah, those two spots there. In order to achieve this desired filtering, let's take a look at some of the basic fundamentals that compose the whole algorithm. Starting with nonlinear passing. So linear approach, treat every pixel with the exact same convolution, right? So basically what this means is that, remember that Gaussian filter? I'm gonna keep the exact same thing, run it back and forth, back and forth, back and forth, no matter what I do, right? The nonlinear approach is that treat every pixel with varying intensity, depending on its neighborhood qualities. Ignore the last part. So basically, I want to be able to switch between a wide with a very selective filter, right? How would we achieve this? Remember the heat equation? Yeah, just review, blah, blah, blah. Diffusion is a flow of material with energy. That's just the definition of diffusion. The ideal variable conductance term, C of x of y. We're just going to try to create our own function that behaves the way that we want right now. The term C of x of y controls the rate of flow and allows it to be defined differentially in each part of the image. There was, let's see if I can go back. There we go. For additional information, contact that. Yes. What's up?
Yeah, I have a question, please.
Sure.
Sorry to interrupt you. Okay, you are working on your subject. Your topic is on.
Anisotropic diffusion.
Okay, but now you are applying the heat equation to reduce the noise on the
Yeah. So.
on the image, basically.
Yeah.
Okay, so to get that done, you use the heat function. Go back. Okay, that equation, heat equation, differential of S.
I think it's on the I don't know if you have it pulled up, the third slide or maybe fourth slide, where I define it in 2D space.
Okay.
This right here, I'm doing heat in the system is equal to the diffusion around x and y, right? It's essentially kind of what it's saying. And A, which is not there, is supposed to be equal to 1, right?
Okay. Okay. So which parameter on the heat equation, because that differential of F it is the image, right?
Which one?
Okay, no. Input image I, output image sequence. Okay, F it is the output image.
Yeah.
Heat equation. Okay, continue. Let's go.
Yeah, so like after I diffuse, I'm gonna get an output image, right?
Let's go.
Okay, cool. The term conductance, sorry, I lost my place. Conductance term is defined by C x of y. Okay, so let's implement this specific nonlinear approach. We need a detector to tell us if x and y is part of the edge or not. Luckily, the gradient of the brightness function is quite good at that, right? So if I have, you can think of this, if I have a black plane right here and then a white line right there, the gradient's going to jump up significantly, right? Because there's a difference, right? So if I was to think of that in 3D space, the gradient's flat right here at black and then it jumps up straight. Okay. Filter that blurs the inside of the region but skips the edges in the image. So basically, if x and y is part of the edge, then apply very little smoothing. If it's not part of the edge, then apply full smoothing, right? Reminder of what the gradient is. So as you can see here, the first part, the gradient vector is 0n, while n is everything less than 0. This right here. So if you look, this is the gradient, this is normal to the gradient, normal to the gradient, right? So that basically tells us where an edge is located. Points where the normal of the gradient is high could be treated as edge points and therefore be applied less blurring. That's the normalization. Right? Sorry, I didn't mean to. No, right there. Did I skip slides? No, okay. Until now, we have an edge, not edge estimation of what E is. We're just going to call E our filter, which is the L'Hopital's transformation of the image, which is just the word escapes me. I'm sorry. Magnitude. There we go. Okay. Sorry, the words escaped me. We create a G function that controls the blurring intensity according to the normalization of E, right? So the normalization. So if I find an edge, treat it less. E for edge, right? G has to be monotonously decreasing function Y. Because as E approaches the edge, the rate of diffusion is decreasing. Right? So here's G. So we have two different equations for this, right? This is a nonlinear function, right? Linear function would just be a straight line. These functions behave like that, right? Like an E function. So you could say 1 over 1 plus the normalization of E over K squared would be a possible solution, right? Here are my two ideas, or graphically interpreted. Now we have E and G. Let us define the coefficient. The coefficient controls how much smoothing is done to X, Y. So we're going to say our conductance is equal to G, the normalization of the gradient. Simplification, if C, X, Y of T is large, then X, Y is not part of the edge. If C, X, Y, T is small, then X, Y is part of the edge. Makes sense? Ralsberg's idea, C, X, Y dependent only on the data, aka image gradient, and not on the solution F. So, the primary image you have, I'm only paying attention to that gradient, right? Not the result of that gradient. Does that kind of make sense? So after I do my filtering, it's the original gradient, not the filtered image gradient when I do multiple iterations.
Okay.
So here's an example of my conductance with a K parameter, the normal of the vector. So is it still linear? Why or why not? Anyone? No, because the function now.
Before we get to that point, I want to summarize here a few important points, like idea points, that you get the overall picture first. So the overall picture goes like that. What is heat equation doing to the image? You have image, and every pixel in image is changing its value with iterations of the heat equation when you're solving it numerically. Technically, you're solving any differential equation in computer vision using some numerical tools. So derivative, you're replacing it with difference, and so on. So you're solving it in numerical sense, right? So you're doing some kind of iteration on that image. So one pixel will go up, another pixel will go down, but based on what? This regular heat equation, it will look just on the neighbors. If you have very high neighbor, which is like very bright color, which means in terms of heat equation, it means like very hot pixel, okay? This neighbor will grow, so pixel which will be near some hot pixel will grow a little bit, and that hot pixel will go down a little bit, because it shares its own heat with neighbors, right? So all of the neighbors will get a little bit more heat, and the highest ones will get a little bit lower. This is how diffusion happens in iterations, and each time the hottest ones will get a little bit lower, and neighbors will get a little bit higher near those points, focal points of heat, right, or bright colors. So this is how heat equation with iterations, with multiple iterations, will more or less get to average of heat. So it's trying to get to complete blue, which means all of that will be a single average color, right? This is the point of heat equation. Now, when you have also Grossberg idea, he said, why we should do the same thing for all those pixels, right? Because we need to define where we have edge, and then those pixels behave differently somehow. How differently they can behave. This is how it works. Let's say you know where edge pixels are, which we really don't, but let's assume that you have that knowledge and you know where those pixels are. Those pixels should not change at all, right? You don't want to glue edges, right? This is the most reasonable thing to do. Just leave them alone. Just don't touch them. Where you have edge, if you know that this is edge, just don't touch this region or neighborhood. If you know that this is flat neighborhood, just average it all, like make it completely flat, which will produce some sort of cartoon-like image, right? Where you have like single color, then big edge, then again single color, again big jump. So this is cartoon-like images. So his idea was, let's use just small neighborhoods for edges, if you know where it is, and big sigmas where it's completely flat. But how do you know if it is flat or edge? By magnitude of the gradient. If magnitude of the gradient is big, which means this is big jump in numbers, just use really tiny Gaussian sigma, which means don't blur it at all, don't touch it, like leave it as is. If you have very low magnitude of gradient, which means it's flat area, kind of, then use very wide and broad Gaussians there, okay? But you can achieve the same thing with heat equation. How you do that? How heat equation works generally? It has constant C coefficient, and C coefficient is conductance. What is the meaning of conductance? Meaning of conductance is how much it's basically a property of the material. So you know that some materials conducting very well, like metals, for example, and some materials are not conducting almost at all, like silicon or wood or other materials, right? So C is a property of the material, how well this material is conducting. So you can basically put some materials in some places in the image and some other materials in some other places. How do you know which material to put where? For edges, you don't want any conduction, which means you put wood there, okay, with very low conductance coefficient. So you're not conducting anything. From that point, it will be high gradient, leave it alone as is. You put wooden edges, okay? In flat regions, you want to put metal, which is conducting very well. So it will conduct very fast everything around. It will spread around and average on everything, right? So the temperature around will become just average of the neighborhood. That's it. And wooden parts will not be touched. So technically, where you have high magnitude of gradient, just put C, which is very, very low, right? So you want very low conductance where you have edge, and you want very high conductance where you don't have edge. So when this one is magnitude of gradient, if this is like axis of magnitude of gradient, you want when it goes up, which is higher and higher and higher, you want C to become lower and lower, but definitely not negative, because C should be positive, right? So it's some positive number. So the functions that you could think of is that kind of function. It's just starting somewhere and going down with increasing magnitude of gradient, right? So they propose just a few simple ones. It's like hyperbolic kind of function, which is going that way, or exponentially decaying function, which is also going something like that. Okay, that kind of functions. So when magnitude, which is on x-axis, is going higher, magnitude of gradient is becoming higher, C coefficient becoming lower, because this is a function of magnitude. And then conductance will be automatically defined by closeness of edge. Okay? So this is his overall idea, just don't conduct well when you're close to edges.
You can kind of already answered that. So here we're actually kind of looking at it. There's the original image. There's a linear filter. And here's Grossberg's algorithm, a nonlinear filter. Kind of look right here at the edge, it's still very noisy, right? So that's just me saying, like, when I got really close to it, ignore it, right? So I still have all the noise right here at the edge, but it actually has pretty good definition for the most part, for what it is. So interregional smoothing, good. Generally keeps the edges where they were, not much, don't do as much interregional smoothing because they're not in the same region. This might be a part of the solution, but it's not good enough on its own. Edges still stay really rough, so if you look at it, it's still pretty rough. This happens because the kernels shrink the closer it gets to the edge, blurring less till they only care about the pixel is filtering. So basically the filter right here just becomes really, really selective and only cares about the filter right here. So if I had a 1 surrounded by a bunch of zeros on a matrix and I was running that across an image, so like in a Gaussian, I'm only going to pay attention to the pixel I'm actually on, right? If that makes sense. Kind of. So let's go to a MATLAB example. Okay, so here you can see linear blur with Gaussian, right? If you look at this edge right here, you actually get a lot of blurring, right? You get some of the buildings in the background, you actually get a blurring across this edge. Not as much definition as it was here. But if you come down here with Grossberg's, you actually get a lot of definition. See? I mean, the noise is still there, so you see all the kind of dots on it. You can see it that well right here. Yeah, I see dots on my screen. You might not be able to see it on yours. But they just are, they're still there, right there on that line. If you guys want, you can probably run it on MATLAB on your own computer and get a lot more definition. Also, you can switch it between any image you want, and the size of the kernel and anything. This is how I actually was able to do it. Just a minute. Okay. I want that. There we go. Talking a little bit faster than I should be. I should really slow down, but you know. Okay, warning, this following may strengthen your intuition of the flow of the smoothing process. So, program, right? The model and Anisotropic diffusion. We're going to propose a nonlinear form of the heat equation, where C is a function of the solution's gradient magnitude, not the image gradient magnitude. So with successive iterations of an image, I get less and less magnitude, right? So like Dr. Nonlinear was saying, the gradient should be very distinct at the very beginning, and it should slowly start to shrink. Replace I by F in the previous filter, so that diagnosing applies also for the diffusion. So in the previous equations, I believe we have E, but now we switched with F.
So you're just replacing I with F.
I.
So F is every time you get new iteration on F, right? And in Peronomalic compared to Grossberg algorithm. In Grossberg, you're just using constant, and this is why this equation is still linear, called linear equation. Because you're using gradient of I, which is always constant, right? So you can compute it offline, all of the gradient and magnitude of gradient everywhere for each pixel, and you can store it offline somewhere. And then you're using for every iteration in the Grossberg, you're using the same magnitude of gradient of the same original image that you had, which is noisy or whatever. Now, their idea, one of the first ideas that they have, is let's replace that gradient of I by gradient of iterations that I have right now, which means recompute gradient magnitude every single iteration, which is computationally more expensive naturally, but since every time the image becomes smoother and smoother, right, because this is what those iterations are doing, blurring the image, making it smoother, each time you will get better, cleaner, less noisy magnitude of gradient. And then use that one as detector of edge for your purposes of computation of C coefficient. Okay? This is the overall idea number one in that one.
Okay, cool. What changes the function from Grossberg? The norm is now calculated using solution gradients. Okay, cool. Looks pretty much exactly the same, right? I is changed to F. Use varying smoothing kernels. So here's an image I got. You see how I get no noise right here on this edge, and diffusion as it goes in. So I'm actually distinguishing all along my edges and still diffusing within an edge, within depending on which way I approach this image. So upon the x-axis, I have an oval-like kernel, and the closer I get to an edge, the smaller it gets, and then I approach it by a y-axis, and the closer I get to that edge, the smaller it gets. And the more iterations I do, it gets more and more defined. You should be able to see it more accurately in the next images.
So technically this is what anisotropic means. Anisotropic is not equal to all directions.
Yeah.
Isotropic or isotropic is like ground. It's equal in all directions. Anisotropic is different in different directions. So it's aligned with the edge.
So, like you said, isotropic, anisotropic, it's depending on the edge. So here's the original image on the left-hand side. And when I do anisotropic diffusion, you see how all the noise within the image right here, let's say, actually gets blurred together. Right over here, see? You get a little bit more blurring within that region, that edge region. Here's another example. So here's the original, remember that we went over at the very beginning. So here's a linear isotropic diffusion, simple Gaussian, right? I'll pass this image through, you actually get blurring across the entire image. Just kind of that. Nonlinear isotropic diffusion, edge skipping. So I'm skipping over the edge. So if you look right here, I still have noise along this edge, right? But I'm just skipping over it, so it gives me more definition. And here's with nonlinear anisotropic diffusion. So if you look at this edge, I no longer have noise in it. And every iteration of this image I do over and over again, it gets more and more defined. Parameters, amount of blurring is real T, which is related to sigma. K is a free parameter intensity space, which controls the degree in which delta, or log times F, impacts the conductance. K is the contrast of the edge to be preserved. Enhancing edges is indicated by normalization of F is greater than K. The problem with this is that it's kind of difficult to tune in the chicken and the egg problem. It will need multiple iterations to fix. Each pass makes the image better than the last, right? So here is...
Before that, maybe we'll make a short break.
Sure.
10-15 minutes, and then we can continue. Do you want me to turn it off, the lights?
It's up to everyone. I'm pretty good with lights on and off. Someone's taking a nap, so I don't want to interrupt about it. Don't worry about it. Write K as a unit of root mean squared. I'm sorry to jump this in. Hello, back from your break. Congratulations. So what we just went over were the parameters. We talked about the chicken and the egg problem. The gradient stay the same, so we're going to write K as a unit of root mean squared. So my conductance is equal to E, did that jump, right? Where this new thing right here, the normalization is the root mean squared of the gradient magnitude. The entire image some neighborhood. So essentially, I'm blurring within the same neighborhood. So the edge, since they're exactly the same along an x/y axis, we'll call it, depending on which way the line's tilted, I blur along within the edge. So that gets rid of the noise within that edge. K is unitless, like that.
Maybe before that, just why we need all of that. Technically speaking, magnitude of gradient dependent on the image, right? So the range of values that you will get from magnitude is different for different images. If your contrast of your image is very high, you may get very huge magnitudes. And if your contrast is very low of the image, you might get really tiny magnitudes, right? So how do you know, like, you don't want to tune it for every image separately. This is the problem, is that you want to apply the peronomalic, and you want to put the coefficient that you are putting there as something normalized, which will be the same for each image. right? So you want some parameter which will be independent of the image instead of playing with the parameter which is dependent on the image. And that parameter which we had before that K, which was one of the formulas before, it's just in all of the previous, in this one, next one, yes. So that small k, you see that k squared in every formula, which is parameter of the problem. And this parameter actually says where this break lines happens, like where curvature happens to that plot, to any of those plots. So for different k's, you'll have different plots, technically speaking. Now, how you choose which k you want? 1, 2, 4, 55, like which one you want? How you choose that parameter? This parameter dependent on the range of magnitudes that you have in your specific image. But you don't want it to be specific to specific image. You want it to be generally applicable to any image. So the idea is very simple. The idea is let's compute something which is invariant to every image. And what is that? This is root mean square of the magnitude per image, which is easily computable. So you're computing it one time and you have some image, and from that you have the average gradient value. So you normalize it by the average of gradient on all of the image. So if the image has very huge differences, which is like big contrast, great contrast, right? This magnitude will be high. Like if you have a lot of changes, like black and white kind of picture, you will have big value for that root mean square value of magnitude of gradient. If this image is kind of, all of the image is kind of gray, low contrast, most probably this value will be very low, because not much change happens in the image, right? But when you're normalizing, like dividing by that number, it will give you all the time the same range of values for that coefficient k. So your k will be unitless. It will not be anymore in units of magnitude of gradients. It will be just unitless. It will be all the time the same range, between like 1 and 5, no matter what image you have, which is much easier to tune. So you know at least order of magnitude here.
What he said. Rule of thumb, choose a k between 1.5 and 5. Choose t to be approximately 1, which is 4 to 5 iteration for diagnosing, and choose t to be approximately 2.5 for very smooth results. The equations that I do for MATLAB, it functions a little bit differently, but he's basically talking for this for implementation for his code, which I think I might have accidentally removed. So we're going to smooth the gradient first. Okay, the image must be smoothed during every iteration, and only small sigmas are practical. So let's do a MATLAB example. So here is Anisotropic Diffusion. Here is the function that I'm calling, right? It's basically me just setting up how it functions, kappa and everything else in the world, right? So we're going to run this. I left this 200. I didn't mean to do that. So we're going to get a really terrible image. So we're going to set this back down to, does anyone remember what this used to be?
45.
Control Z. Okay, let's try this again. So when I do 1, I'm actually applying the 2 different methods for iterations. So, sorry, let me go back to it. When I pick 1 or 2.
Sorry, you see in that picture, for example, building behind that cameraman disappeared, you see?
Yeah.
But if you will change the k value, you can decide that you want to see it. So based on that k value, basically it means which you will accept as h and which values you will not accept as h. So playing with that k value, you can get back your building if you like.
So let's, where am I? So all I did was switch the k value. 5. Let's run this section one more time. This is after 200 iterations. So if I was to do the exact same iteration for, see, there's the building now. Right, it's a lot more defined. So using Dart and Outline's reference, we'll get down here.
Is there more details?
it gets you more, I mean, you're accepting more edges as edges
Yeah.
and not as flat regions. You're flattening everything above some given threshold, and this K is somehow proportional to the threshold.
So, like you said, K right there. There's my new image after I apply my diffusion to it. After 200 iterations, I think that looks pretty good, right? A lot of this noise right here, you can see these stripes up here,
Yes.
is all gone, right? But you still have great definition. So if I was to do the exact same thing with Gaussian, it would look completely gray. If I was to do the exact same thing with isotropic diffusion, we'll have a few slides later on to talk about this. Isotropic diffusion, Grossberg's model, I'll get a lot of blurring here. I'll lose a lot of definition. I will still kind of get like an outline of it and a general cartoonish picture of it, but nothing near this definition. So let's see. Let's switch it back to 100 iterations. We can see the same image one more time. And then I'll switch the method values. So do that same thing. So 100, this seems pretty good. You can still kind of make out, I don't know if you can on yours, but there's a change in edge right here, just a little bit now. Not nearly as much as it was on the other one, because, or it's a lot more defined on this one, only because I'm using less iterations to define what my edge is. So let's go to 2, which I'm just switching in between my two methods. So my other method, just to be clear, that I'm switching to is this. I'm going to try to show that it's exactly the same thing. Or, you know, ballpark. Just it. And stuff. So, basically the same thing, right? Kind of. So let's step down kappa. See? 3.5. Run it again. There we go. It's pretty good, right? Let's see. That's just because they're both basically the same thing. They both function the exact same way. You see this part right here.
This method. I don't think the images are the same. Like the edge was different. You can come back.
Let's do this.
Just from the first method and the second method.
Okay.
So they are clearly different.
Well, he's
The results are
Yeah.
clearly different, but
He said
They
it's
function
same.
exactly the
But
same.
they are not exactly the same. I mean, they are different.
Yeah.
Because one is exponent, another one is hyperbolic, which means one has more curvature going down, which is cutting more strongly the edges,
Yeah.
like it's more stronger threshold, and another one is more kind of soft threshold.
Because one,
So-
the edge is gone. They took all the edge.
Let's see if I can't do this.
Change it to 3. We change the number to 3.
Which one?
Subplots. We got 1, 2.
Yeah.
That one should be 3.
Correct.
Goes by order. 1, 2, 3.
Do I use it? Let's see what's happening. Right now, they're trying to share the same variables. Once it's loading up, it's not letting me. So we just have to compare them side by side. So let's switch this to 25 or 5, I would just say. There we go. From that. It's the same. Exponential. This one's switching back to 1. 1.5 actually. So more selective. And I'm switching this to 2.
Figure maybe. Add a figure.
Or,
Say figure, then run it.
What is a subplot?
I changed my kappa value. They both, they're functioning similarly.
So,
Okay, maybe I shouldn't use the word exactly the same. I'm changing my kappa values, right? So this one, I'm trying to be a little bit more selective with the edges, but I'm trying to say like they both, I don't want to say function exactly the same again, but they're blurring along with the edges, and they're both,
leaving the edges.
yes, okay.
They did the same idea.
Form the same
Maybe I shouldn't have said exactly the same in the same manner, because when I said, because if I switch this over to 5, for example, which was the value for the other one, a lot less sense.
Edge is gone.
Yep, so it flips out just a little bit.
Edge is gone.
See how I got weird blurring down here. It's just kind of how it goes. In fact, if I go to 25,
Do the same thing.
and it's a lot less selective. Kappa, kappa. Okay.
So now, that K.
Yep.
Okay, how, if I don't have the, so what are the parameters that are involved on the choice of that K? If I don't have the image origin when I already apply, where I already applied the mask or the filter, how to choose the K?
So you have multiple. First of all, simplest one is just pick and choose whatever you want. Just play with the parameter, trial and error. This is the simplest method. Now, to that method, you have also improvements, okay? And this is exactly the improvements that we are talking here about. How you can simplify your choice. If you're using that method, which means before you apply that K, you divide it by the average root mean square kind of value of magnitude. That K, then K should become between like 1 and some other number like 5. This is effective value. Which means if it is 1, it will leave technically all of the edges, even noisy ones. If it is close to 5, it will remove almost all of the edges but the strongest ones. You need something in between, depends on how many edges you want to leave. Like if you're really interested in details, in detailed edges, then keep it pretty small. If you want just cartoon-like overall image of just general contour of the body, and not details of like jacket and other stuff like that, or eyes or small details, right? If you don't care about those small details, just choose it close to 3, 4, right? Something of that range. So it depends on what you want to get.
Here's a histogram of it. Select K for every iteration, compute the histogram of normalization of an H. So find K such that 90% of the pixels have a gradient greater than K. Right.
So what this assumes actually? Can you guess? Like why they say 90%?
No,
No. So they say something like that. Choose that threshold, that 90% of the magnitudes will be within that range. And this will be your K value. Like choose such a K that it will include 90% for complete blurring. Why 90%?
The edges, they don't.
So the background assumption in that kind of improvement is that about 10% of the image are edges. This is what it assumes technically. Like, maybe it's right, maybe it's wrong, it depends on the image, but this is overall assumption.
This is an example of actually the 90%, right? So there's a first iteration at 10. You see how it's just getting kind of blurry. I'm trying to be more homogeneous. Then there's B at 20, C at 50, and D at 100, right? You get this kind of cartoonish-like image, and everything else is just completely blurred in, right? His belly was white furred, not completely blurred, completely white furred, and his eyes are completely black, so. Here's some more examples of it, the original and the diffusion. And you kind of see, you can't see my mouse. You
can't, you have to drag it like that, right?
Well, that's permanent now. Okay, anyway. I guess you can pay attention to that little area right there. You see how it just kind of fuses? That wasn't a very strong line, so I'm assuming the capital wasn't that high. Or the capital was high enough to exempt that line. Additional information is here, some brain scans. We're going to compare previous methods. So here's the linear isotropic diffusion. So we Gaussian, right? More and more blurry and kind of equalizes out after 40 times, right? If I kept on going out to 100, it might actually equalize out even further than that. Nonlinear diffusion, so this would be Grossberg's. The previous one, you can't even make out this line, right, at 40 iterations. But this one, since you're not doing any diffusion right there, it kind of preserves it just a little more, right? There's still noise right there, right? But you actually preserve it. Let's compare it to. Go just one slide ahead. Forgot. There's the, I wouldn't even say that's the original image, but this is closer to the original image right here. But you see how it's just progressively more blurry. You can't even see the outline of it anymore. This way you can still see the outline from that 40. Let's go through anisotropic. Nonlinear anisotropic diffusion. So there's at 0, and here's at 40 now. You have almost no noise right here. I'm sure if I could go even further out, I get no noise whatsoever, but it's pretty good, right? So if I would do a Sobel filter on that, I should get very distinct lines. And let's compare the two. You see how it's kind of blurring right here, areas where it's very close to each other. And still get very distinct patterns right here. So, here's my sources, Dr. Nonlinear, scholarly articles, and a bunch of YouTube videos. I'm gonna watch. Keep the annotations. That's pretty much it. If you want to stay after, we can run more of these images. So diffusion extra, I think, is actually one I wanted to run. Okay. So let's play guessing game. Anyone care to tell which filter is which? Don't worry, it's going to be pretty hard to tell. I think. Let's see. I can't. Yeah. So,
Okay. That one,
first one.
that one is anis.
Anisotropic.
Yeah, which T? I will say T10 or 4 or something.
It's like, I think it's 40 is what I said, 2 or 50.
Okay.
No, that's actually 100, sorry.
300.
100.
Ah, 100, okay.
Right. So let me make sure. Yep, 100. Right.
Okay.
Yeah, that's right. You don't see the answers. What's this one?
Just linear 100.
That's right there is Gaussian filtering, but yeah. So I'm just using a larger kernel for that one. No,
Okay.
no iterations. So I believe I use a 8x8. No, it's a that you can see this distinction of lines right there. So it's probably a filter that's more closely locked into 1.4 than 1.8. Yes, I know, but yeah, 4.1. There we go. Now, this last one. Grossberg's, right? So like if you look at the edges, I still have a lot of noise in there, right? But everything else is just slowly becoming more and more blurred. Right? Let me check to make sure, so I'm not scaring what you guys are wrong. Yeah. Grossberg. Cool. We mess around with the filters if you guys want. So anyone want to give me how many iterations I should do for this anisotropic?
2,000.
3,000.
5,000.
I don't
9,000.
Now you will blow up.
You know, we're going to be here for a little while, and I'm not going to invest with those because we're just going to do the 40. Okay.
42.
3,000. So, while this is ticking up for the next hour, burning up time, thank you for this.
Well,
Next, we'll try 5,000 successful iterations of that, Fibonacci sequence and everything else for that.
Yep.
So, what do you think will happen?
It's gonna be
Picture
blooming.
will show up.
you know,
Picture
smoke off
will
the
show
magic.
up. If you look, I accidentally set the cap at 25. So let's take a fun guess before it actually gets to 3,000, which thank God is for fall.
I don't think we should.
Nothing will show up. You think it's just going to be complete blur, right?
Everything.
You think it's going to be kind of cartoonish? Maybe like a weird looking squirrel? Maybe a squirrel will pop up. That would be a fun trick,
Oh, this is the cameraman.
right? Yeah, this is the cameraman. I don't know. Maybe a squirrel will pop up in the background. I don't know. Drum roll.
Thulu
And
will show up.
I think it.
You have to open that.
Ah,
Look at
great
that.
portrait. Art.
It looks. See, I kind of still have. I can kind. No, I can't make out anything.
It's a
Why?
shadow
K
of the
equals
shadow.
why?
So
Yeah. Okay. K equals 5 at 3,000. I can easily.
Yeah.
I didn't want to stop it. I already had so much time invested to 3,000. Like, this would be interesting. Let's make this look cool. This is, I believe, method 2. So this is 1 over 1 plus K, or 1 over 1 plus the normalization of the gradient over K squared, right? That's method number 2.
So basically a bunny rabbit.
I'm hoping if a money rabbit pops up, it'd be the coolest thing ever.
Sir, I have a question.
Next time we're not going to do 3,000, by the way.
In those, this kind of, I will say, with those kind of filter, there is any calculation on that use the entropy of the image?
This is based only on the brightness values, not entropy. And magnitude of gradient.
Okay.
So, if you guys noticed, the camera's gone. Up in the camera.
Oh, it's almost segmented whole man on it.
Right? It looks pretty cool.
That's good.
What?
Useful. Thank you.
I think it looks pretty cool. It's like the squirrel thing.
So if we go to 9,000, you just segment it to me.
I'm not doing 9,000. Okay. Since you guys sat through here and let me mess around just a little bit, we're going to run this super secret surprise one. Okay, you guys ready? Start. Look, there's glasses right here. You can see a little reflection. It's kind of scary. I saw this and I started panicking. Right? It's like, oh god, you can see if you're alive. It's panicking. But you can legitimately do this to any picture you want. You can blur edges. You can crop things into it, blur it, make it look. Actually, there's actually a guy on YouTube that does this for fun with celebrities and whatnot. It's like super funny. I think I have it in one of my sources. If you scan through that. But yeah, thank you very much for sitting through this and letting me mess around at the very end.